Hello, welcome to section 1.6 of the course M132 Introduction to Linear Algebra. This section is the last one that we will cover in chapter 1 from the book, and the title of this section is Determinant of a Matrix. In other words, we will learn how to calculate the determinant of the matrix. This section is sort of divided into three parts. One part we will discuss how to calculate the determinant of a 2 by 2 matrix, then how to calculate the determinant of a 3 by 3 matrix and higher. Finally, we'll talk about properties of determinants, and we will do some applications on this section. To begin with, let's look, as we said, at the how to find the determinant of a 2 by 2 matrix. The determinant of the matrix A, in general, A, B, C, D, denoted by absolute value of A, or determinant of A, is given by AD minus BC, as can be seen from the sketch here, AD minus BC. Examples: if A is equal to a 2 by 2 matrix, 3, 4, minus 1, 2, then the determinant of A is equal to 3 times 2 minus 4 times minus 1, which is equal to 6, plus 4, which is equal to 10. To find the determinant of a 3 by 3 matrix, let's take a general matrix, a 3 by 3 matrix, with elements A11, A12, A13, etc. to A33. The determinant of A, if we expand along the first row, is as follows: A11, which is the first element here, is multiplied times the determinant of the minor. The minor here is obtained by eliminating the first row and the first column here. And the minor is A22, A23, A32, A34, minus the second element here, A12, times the minor, which is the determinant of the minor, which is obtained by eliminating the first row and the second column, which is the determinant of A21, A23, A31, A33, plus the last element here, A13, times the determinant of the minor obtained by eliminating the first row and the third column, which is the determinant of A21, A22, A31, A32, as can be seen here. Okay, let's look at an example. If A is equal to 9, 8, 7, 6, 5, 4, 3, 2, 2, which is a 3 by 3 matrix, then the determinant of A, designated as the matrix as it is in absolute value, is equal to 9 times the minor. The minor is 5, 4, 2, 2, minus 8 times the minor obtained by eliminating this column, the second column, and the first row, becomes 6, 4, 3, 2, plus 7 times the last minor, which is obtained by eliminating the first row and the third column, 7, 6, 5, 3, 2, the determinant of 6, 5, 3, 2. If we do the operations, we have 9 times 2 minus 8 times 0 plus 7 times minus 3, which is equal to minus 3. Properties of determinants. We have several properties. The determinant of a matrix and its transpose are equal. That is A transpose. Determinant of A transpose is equal to the determinant of A. Example: 1, 2, 3, 4, or 1, 3, 2, 4. These two matrices are transpose of each other, and the determinant is equal if we apply the rule of AD minus BC. This rule can be transposed or can be projected to 3 by 3 and 4 by 4 or higher order matrices. The second property: if a matrix B results from a matrix A by interchanging two rows or columns of A, then the determinant of B is equal to minus the determinant of A. In other words, every time we interchange rows or columns of a matrix, we multiply the matrix by a -1, as seen here. If two rows or columns of a matrix A are equal, then the determinant is equal to 0. Example 1 2 3 0 1 4 1 2 3. Here we notice that this is a 3 by 3 matrix, and the first row and the last row, third row, are equal. Therefore the determinant is 0. The second property here, if a row or column of a matrix A consists entirely of zeros, then the determinant of A is 0. Any column of row, here in this example here, the second row has elements 0, therefore the determinant is 0. If two rows or columns of the matrix A are multiple of each other, then A is equal to 0. Here in this case, we notice that the first row and the third row are multiple of each other. In other words, the third row is obtained by multiplying the first row by 2. In this case, the determinant is equal to 0. If a matrix B is obtained from a matrix A by multiplying one row or column of A by a number R, real number R, then the determinant of B is equal to R times A. Example, if we have a 2 by 2 matrix, the determinant of this 2 by 2 matrix, 10, 20, 3, 4, is equal to 10 times the determinant of the matrix 1, 2, 3, 4, which is equal to 10 times minus 2, which is equal to minus 20. Another property, if a matrix B is obtained for a matrix A by adding a multiple of one row or column of A to another row or column of A, then B is equal to A. Determinant of B is equal to determinant of A. Example 1, 2, 3, 4. Let's do row 1 plus 10 row 2 to obtain the matrix on the right hand side, 31, 42, 3, 4. Then these two matrices have equal determinants. The determinant does not change. More properties. The determinant of an n by n upper or lower triangular matrix is the product of its main diagonal entries. In other words, this 3 by 3 here, example, this 3 by 3 matrix that we have here, the determinant is obtained by multiplying the elements along the main diagonal, 1, 2, 4, which is equal to 1 times 2 times 4, which is equal to 8. And as you can see, this matrix here is an upper triangular matrix. The same can be said if the matrix was lower triangular. The determinant of an n by n diagonal matrix is the product of its main diagonal entries. Here, as you can see, we have elements only along the main diagonal and the rest are zeros. Therefore, the determinant is equal to the product of the elements along the main diagonal. More properties. The determinant of A times B is equal to the determinant of A times the determinant of B. The determinant of A to the power n is equal to the determinant of A to the power n. In other words, if we have A to the power n that we need to find its determinant, this is the same as doing the determinant of A and raising it to power n. The determinant of an inverse of a matrix is equal to 1 over the determinant of the matrix itself. If A is an n by n matrix and R is a scalar value, then R times A, the determinant of R times A, is equal to R to the power n, since the matrix A is n by n, times the determinant of A. A is non-singular if and only if the determinant of A is different than 0. Non-singular means it is invertible, has an inverse. Let's look at examples. Example 1. We have this matrix here which is 4 by 4. We are being asked to evaluate the determinant, calculate the determinant. Here we start off by copying the determinant, copying the matrix the way it is here. Then we interchange row 2 with row 3. All we have to do is interchange these two rows. And we have learned from previous slides that whenever we interchange rows or columns, the matrix is multiplied by -1 or is changed sign. So when we do this, we have minus here on this side, the determinant of the matrix as we can see here. Now this matrix here has become an upper triangular matrix, and by the rule that we have seen before, The determinant of an upper triangular matrix is obtained by multiplying the elements along the main diagonal. We have a minus here, which translates to minus 1 here. 2 times 4 times 3 times minus 1. This is equal to 24. More examples. If A and B are 5 by 5 matrices, 5 by 5 matrices, 5 rows and 5 columns each, with the determinant of A is equal to 8 and the determinant of B 2. We're being asked to find the determinant of A to the power 2, the determinant of minus A, the determinant of A transpose times B minus 1, and fourth, the determinant of 2 times A minus 1 times B to the power 4 times A. Let's start off by calculating the determinant of A to the power 2. A to the power 2 is the same as we have seen before from the rules or the properties, is the same as calculating the determinant of A arranged to the power 2. But we have the determinant of A as being equal to 8. 8 to the power 2 is 64. The determinant of minus A is equal to minus 1 to the power 5, since A and B are both 5 by 5 matrices, times the determinant of A. Minus 1 to the power 5 is minus 1, and the determinant of A is 8. Minus 1 times 8 is minus 8. Thirdly, we need to calculate the determinant of A transpose times B minus 1. This is equal to the determinant of A transpose times the determinant of B minus 1, but the determinant of A transpose is the same as the determinant of A, and the determinant of B minus 1 is equal to 1 over the determinant of B. The determinant of A is 8, the determinant of B is 2, 8 over 2 is 4. Therefore, this translates into determinant is equal to 4. Finally, calculate the determinant of 2 times A minus 1 times B to the power 4 times A. This is equal to 2 to the power 5, since the matrices are 5 by 5, times the determinant of A minus 1, times the determinant of B to the power 4, times the determinant of A. 2 to the power 5 is 32, times the determinant of A minus 1 is 1 over the determinant of A. The determinant of B4 is the determinant of B raised to the power 4, here, times the determinant of A. The determinant of A and the determinant of A then cancel each other, which is 8 and 8, they cancel each other. Determinant of B to the power 4, it's 2 to the power 4. This is 32 times 16 is 512. More examples. Answer each of the following as true or false. Justify your answer. Part I. If A and B are n by n matrices, then the product A times B, the determinant of the product A times B, is equal to determinant of the product B times A. Part I. If A and B are n by n matrices, then A plus B, the determinant of A plus B, is equal to the determinant of A plus the determinant of B. Part I. If A and B are n by n matrices such that AB to the power 2 is equal to IN, then A is non-singular. A is non-singular, it means is invertible, which means has a determinant that is different than 0. Okay, let's look at the first one. Part I. The determinant of A times B is equal to the determinant of A times the determinant of B. Since multiplication is commutative, this is the same as the determinant of B times the determinant of A, which is equal to the determinant of B times A, which is true. Part I. Let's address this problem by taking a particular example. Let A equal 1, 0, 0, 2 and B equal to 3, 0, 0, 4. A plus B is equal to 4, 0, 6, 0, 6. A plus B is equal to 24. Determinant of A plus B is equal to 24. Determinant of A is equal to 2. Determinant of B is equal to 12. Therefore, the determinant of A plus B is different than the determinant of A plus the determinant of B. Lastly, determinant of A times B to the power 2 is equal to IN. If we take the determinant of both, that means the first one here we can split it as being determinant of A times determinant of B to the power 2. which is equal to determinant of I. Determinant of I is equal to 1. Therefore, A times B2 is equal to 1, which means that A is different than 0, which is true. A is different than 0, determinant is different than 0. That means that the matrix A is invertible, and therefore A is non-singular. Problem number 4. By reduction to triangular form, evaluate. We have to calculate the determinant of this matrix by evaluating, by doing reduction. By reduction to triangular form. In other words, we need to transform this matrix to a triangular form and apply the rule of multiplying the elements along the main diagonal. If we do this, the first thing we have to do, if we copy here, we copy the matrix the way it is, we copy the matrix here, and what we do here is we have to do the elimination first in order to transform these two elements into zeros. So that what we're trying to do here, we're trying to make this matrix as upper triangular. And how we do this is if we do row 2 plus row 1 in row 2 and row 3 minus 2 row 1 in row 3. Doing so, we obtain this matrix here. As you can see, we have zeros here, and this is what we have for the rest of the elements. Now we need to change these two to zeros. We use the second row as our reference, and we do R3 minus R2 in R3, R4 minus R2 in R4 to obtain this. Now we have the matrix here, which is still not upper triangular. We need to change this to 0. But first we notice that we have the third row here, we have 10 and 10. That means we can simplify by taking the 10 as a factor. So if we take the 10 as a factor, we are left with the matrix as follows here. We have 1 and 1 here instead of 10, 10. Now we need to eliminate this. To eliminate this, we use the third row as a reference, R4 minus R3 in R4 to obtain this matrix. Now the matrix is upper triangular, and as we have seen before from the properties of determinants, the determinant of this matrix is equal to 10, which is the factor here, times the elements along the main diagonal, 1 times 1 times 1 times minus 4, which is equal to minus 40. Last example in this section, example 5. If the determinant of ABC, DEF, GHI is equal to 2, find the determinant of 2G, A, 3D, 2H, B, 3E, 2I, C, and 3F. The way to solve similar problems like this is to try to relate the matrix on the right to the matrix here on the left hand side, since we know already the value of this matrix. Let's do that. Let's break it down and try to bring it back to this. If we do that, we have here, if we copy the matrix the way it is here, we notice that we have 3's here. We can take the 3 as a factor. Therefore 3 factor 2G, 2H, 2I, A, B, C, D, E, F here. Then we can take the 2 as a factor here. So we're left with 3 times 2, 6, G, A, D, H, B, E, I, C, F. The determinant of this. Now we interchanged the first column and the third column here. We interchange them together. Every time we interchange column or rows, as we have seen, we have to change the sign. So this becomes minus 6 here. DEF first, then ABC, then GHI. Then we interchange the first two columns, these two. So ABC, we have ABC, and DEF and GHI. Again, when we interchange the two columns, we change the sign again. So from minus 6 to plus 6, as if we multiplied times minus 1. Finally, we transpose this matrix. If we transpose this matrix, we obtain the matrix that we started with and for which we know the determinant. So the determinant of this is equal to 6 times 2, which is equal to 12. This ends this tutorial. Good luck.